Ready for a deep dive? We're tackling particle physics today.
Always exciting. And this time we're looking at anomaly detection that could turn the field on its head.
Exactly. And the best part is, it might not be as complicated as it sounds. We're talking about something called an IRC-safe graph autoencoder.
Yeah, it's a mouthful, I know. But believe me, the idea is actually pretty elegant when you get down to it.
Elegance in particle physics. That's what we like to hear.
Okay, so for those of us who haven't cracked open a physics textbook lately, what's the problem we're trying to solve?
Imagine trying to find a tiny, faint star. Like really faint. And it's lost in the middle of the Milky Way, where everything is just a jumble of light and chaos.
That's a tough one.
You got it. And that's pretty much the challenge physicists face when they're searching for what we call new physics, stuff that goes beyond our current understanding. Our usual methods, they're good at spotting the obvious things, the elephants in the room. But what if the new physics is more like a subtle gravitational wobble that tells us there's an invisible planet somewhere out there?
Precisely. We're talking about finding those tiny deviations, those whispers in the data that might point to something revolutionary. And that's where this research paper comes in. They're proposing a new method, a new way to find those subtle anomalies. And the key, it all comes down to this idea of IRC safety.
Okay, IRC safety sounds like a technical term. Break it down for us. What does that even mean?
Okay, so imagine you're trying to find a needle in a haystack, right? But this haystack, it's constantly shifting and changing because of the wind.
Sounds like a nightmare.
It would be.
Right.
So IRC safety, think of it like a magic net that always catches the needle no matter how much that haystack moves around. It's about making sure we're zeroing in on the real deal, the underlying physics, and not getting sidetracked by random fluctuations in the data. Basically, it's like having noise-canceling headphones for particle physics.
Noise-canceling headphones. Okay, I like where this is going. So how does that work in practice? How do you build those noise-canceling headphones for something as complex as particle collisions?
Well, it all starts with a very specific type of graph neural network. They call it an energy-weighted message passing network, or EMPN for short.
EMPN, right, got it.
And basically what's cool about this EMPN is that it's not just looking at each particle individually, it's analyzing the relationships between them, like how they're connected and how energy flows between them. Kind of like a game of telephone, but instead of whispers, they're passing information about their energy and momentum.
So instead of getting lost in the weeds with each individual particle, this EMPN is looking for the bigger picture, the overall patterns and how they interact.
Exactly. And here's the kicker. Because it uses this energy-weighted message passing, it automatically filters out those low-energy emissions that can muddy the waters, those collinear emissions. It's like it naturally zeroes in on the good stuff, ensuring the final analysis is, you guessed it, IRC-safe. Pretty neat, huh?
It is pretty neat. So we have this IRC-safe tool, this EMPN, that can sift through all this complex particle data. But how do we know if it actually works? How do we know it's finding anything useful?
Good question. So they put it to the test using something called top quark jets. These are like the rock stars of the particle world.
Rock stars. All right, you've got my attention. What makes these top quark jets so special?
They're incredibly energetic.
Okay.
And they have this tendency to produce these showers of particles that can give us clues about new physics.
So they're like little particle factories, these top quark jets.
That's a good way to put it. And they're perfect for testing out this new method because, finding something unusual in a top quark jet, that's a big deal.
A smoking gun for new physics.
Exactly. So they fed all this data from these top quark jets into the autoencoder, right? And get this.
Yeah.
Even though the autoencoder had never seen a top quark jet before, it was able to flag them as anomalies.
Hold on.
Yeah.
It had never seen one before.
Never seen one.
And it could still tell that something was off, that it didn't fit with the other jets it had been analyzing.
That's exactly it. It was like it learned the language of particle interactions so well just from studying those ordinary jets.
Wow.
That it could spot a top quark jet a mile away, even without knowing what a top quark jet was supposed to look like.
That's seriously impressive.
It really is.
It's like, imagine showing someone 1,000 pictures of cats.
Yeah.
And then suddenly they see a picture of a dog and they're like, wait a minute, this one's different.
That's a great analogy. It's like it developed this intuition, this sense for what's normal and what's not, just from the data itself.
So how does it do that? How does it organize all this information? It's like trying to find patterns in a hurricane, right?
Well, that's where the latent space comes in.
Yeah.
So the autoencoder It takes all this complex data, right? The
Hmm.
energy of the particles, their momentum, how they're connected,
Yeah.
and it boils it all down into this simpler code,
Okay.
this compressed representation of the galactic.
Hmm.
And that's the latent space. It's like a secret language that the autoencoder uses to understand these jets.
So it's translating this particle chaos into something it can actually work with.
Exactly. And here's where it gets really wild. So there are these things called energy correlation functions, or ECFs for
Well,
short.
ECFs, right. I've heard of those.
They're a way of measuring how the energy is distributed within a jet.
Yeah, they're like the fingerprint of a jet, right? Each type of jet has a unique ECF.
Exactly. And get this, the autoencoder, without ever being told about ECFs, its latent space, that secret code it came up with,
Yeah.
it's highly correlated with these ECFs.
You're kidding.
Nope, it's like it rediscovered these fundamental principles of jet physics all on its own, just by analyzing the data.
So it's not just finding the anomalies, it's giving us clues about why they're anomalies in the first place.
Precisely. And that's incredibly powerful.
Wow. So where do we go from here? What's the next step in all of this? This is seriously cool stuff, but I think it'd be helpful to take a step back here.
Yeah, totally.
For those of us who aren't, particle physicists, what's the big takeaway here?
Well, it's bigger than just particles, right?
Okay.
This is really about the future of scientific discovery. We're talking about using machine learning to find patterns in these huge, messy data sets, patterns that humans might miss entirely.
So it's like we're giving scientists this new tool, this super-powered magnifying glass, to see things that have always been there, but were just too subtle for us to notice before.
Exactly. And think about the possibilities, right? This could be huge for cosmology, for medicine, even for something like climate science. It's not just about particle physics.
So we're talking about a whole new way of doing science, almost.
Yeah, it's a potential paradigm shift.
Wow.
And the crazy thing is we're only just scratching the surface. I mean, who knows what we'll find as these tools get even more powerful, as we learn to ask the right questions.
Like what kind of questions?
Well, we might find new particles we haven't even dreamed of.
Oh, there are more.
There could be a whole zoo of them out there.
Mm-hmm.
Or new forces, new symmetries of nature, things we never would have thought to look for before.
It's kind of mind-blowing. Like we're standing on the edge of this whole new world of discovery.
We are.
Uh-huh.
And it's a world that could completely change our understanding of the universe
Mm-hmm.
and our place in it.
It's exciting, sure,
Yeah.
but also a little bit humbling, don't you think?
It really is. If there's one thing I want listeners to take away from this, it's to never lose that sense of wonder, that curiosity.
That's what it's all about, right?
Exactly.
Yeah,
Because the universe is full of mysteries and we're just starting to scratch the surface.
I like the sound of that. Well, that's all the time we have for today's deep dive. But don't worry, we'll be back soon with more fascinating stories from the world of science and tech. Until then, keep those questions coming and keep exploring.